So continuing with our discussion around decision-making with probability distributions, the normal probability distribution is probably the most important distribution for describing a continuous random variable. It's the one that we'll be using the most with our data, making assumptions that they are scaled, and we want to have some understanding of how they're distributed across a normal probability distribution, which allows us the greatest flexibility in utilizing it for different kinds of analyses. The actual arithmetic, if you want to calculate it, is there, but I think for this class it's more conceptually important to understand what it means and how it helps us with interpreting things. So normal probabilities have a skewness of 0, which means, of course, the frequency of the mean, median, and mode are all going to be at the same point. Areas under the curve are basically, you can imagine that if this is everything that happens, 0.5 of the proportion of things that are going to be happening are on the right, and the same 0.5 are on the left, with the center being the mean, median, mode. We've looked at these measures of central tendency in a prior session, so it should be somewhat of a review. One of the properties of the probability distribution, normal probability distribution, is that while the shape of it can be the same and is the same, with the measure of central tendency being here in the center, and the highest point of the frequency distribution being in the middle, the shape of it will also be affected by the variance and standard deviation. So here, a variance of 15 versus a variance of 25, smaller variances will give you the shape of a distribution that's a bit more peaked and thinner. Those with larger variances will and standard deviations would produce a wider, flatter curve. So that's one thing to keep in mind, but it doesn't affect really the assumptions that we can make about everything else that's happening with the properties, which makes it very interpretable. The empirical rule still applies, and in fact that's why it is so useful to us. And you may recall that plus or minus 1 standard deviation around the center point, 68.26 of all the observations would be in that space. It can be also interpreted as a proportion, of course. So if you went in randomly and selected some kind of sample, you would expect 68% of the time you're likely to select something within plus or minus 1 standard deviation of the mean. Now that we've learned a little bit more about z-scores, you can see that it's entirely interpretable to the z-score interpretation that we had. So a z-score of 1, 2, or 3 above the mean, or minus 1, 2, and 3 below the mean. That's also a way for us to understand the proportion of things that are happening. And this is just going to be interpreted in terms of measuring the unit around standard deviation of the mean, but it's still very much interpretable. One of the other nice things about it is we're able to convert z-scores into scores, just as we are to convert scores into z-scores. These two are really just mathematically working out and are equivalent to each other. So you could ask the question, what's the z-score for a value of 462, for example, with a sample mean of 434 and a standard deviation of 12. But you could also say, well, what is the score for a z-score at any particular range, such as 0.25 from a sample with those same properties, and you'll be able to convert back and forth. So solving for this is going to give you the 462, and solving for this is going to give you the z-score of 0.25. So we can think of z as a measure of the number of standard deviations around that central point of mu. Here, for this normal probability distribution, we're interested in answering questions like this. What is the probability that some value will exceed a given value or be less than a given value or be between two given values? We could also find out in a value that would exceed a certain level of a probability or be less than a certain level of probability. All of these are kinds of questions that you could ask and answer using this normal probability distribution. You can also find values such as x that will be between different points. So I have a couple of examples that you might read, questions that utilize this. What's the probability that demand will exceed supply by 5% at a certain time? Or to ensure no more than 5% chance of being out of stock, for example, out of some kind of supply, at what point should we resupply? Normal probability is going to be helpful to answer those, and I think we're going to illustrate both of these in just a moment. Taking the case of an amusement park refreshment stand, guests order 5 liters of beverages an hour with a standard deviation of 3 liters. What's the likelihood that guests are going to order between 2 and 8 liters in the next hour? So we have all the information here. To express it in terms of some kind of notation or equality, we're actually answering this kind of a question. What's the probability that we have some value that is going to be between the 2 liters and the 8 liters in the next hour? This is basically just restating what we have in words above. And we know that the mean and standard deviation, it was given to us in this case of 5 liters and 3 liters. This is really all the information that we're going to need to compute a z-score. So the z-score, you can go back and look at the formula, but I just have the values actually placed in here. Any value x minus the mean divided by the standard deviation is going to give you the z-score. And what's new is, while you could continue to try to calculate these things by hand and such, luckily there are tables that we can interpret what's happening in terms of a proportion or a likelihood. And so for that, once you get your z-score, in this case it's -1, most textbooks, or you can find or online a z-score table, and you can look this up. Since I have a negative z-score here, I've reproduced that portion of the table for convenience. And I can see here the way to read a z-score, the rows are always going to be the first elements that are in the z-score, and then the column information is going to be the very last digit. And you effectively put it together to make this whole value. So in this case, the row being -1, and the column being 0, 0, you just put these two together. That's really how you get to the appropriate z-score in the table. And more importantly, here's how to interpret it. So at a z-score of -1, we see the proportion is 0.1587. What does that mean? That would be equivalent to, effectively, if I were to sort of illustrate it using the normal curve, which we have here, this is all the elements that would occur. In this case, it's going to be liters of beverages consumed. And we know at a z-score of -1.0, which is the score of 2, it's basically telling me the proportion of scores, the proportion of frequencies of, in this case, beverages consumed that would be exceeding it, that goes off to the left, is only 0.1587 or 15%, 15.87%. So if I looked at a distribution of this type and I wanted to know what 2 liters represent, which I was able to calculate as -1 on the z-scale, it tells me that I only am seeing values of less than that 15% of the time. Let's go on the other side now and see how we can finish this with the top for 0.8. Similarly, we've computed the z-score here of 8 liters minus 5 the mean divided by the standard deviation. Now this is actually a z-score of 1.0. Well, that's interesting. So I've reproduced the plot here of what that z-score would look like. So going to the tables, I can also see the proportion of scores, and this is where it's important to understand how the z-tables work. The proportion of scores that are again, to the left of whatever this point is. So here with a z-score of 1.0, it come here, it's saying that the proportion of values, the proportion of liters consumed, all of that would be 0.8413 that goes to the left, or 84%. In other words, given this sample of a beverage stand that our guests are ordering beverages, for all time that this sample, if you were to be able to run it, 84% of the time, or 84% of the beverages consumed would be to the left of here, leaving very little actually to the right. And that's we'll get to that in the next example. But our question asked, what is the proportion of time or the proportion of liters, if you will, that we would see in between 2 liters and 8 liters, which is really the value that's in between here. So how do we find that? Well, we need to just do a little bit of subtraction here, since we're basically double counting this part of the tail. So we need to take that out. So if we take the larger proportion of 0.84, subtract the first one that we found of 0.15, and we would get the value of 0.682, which is very good, because we know this from the empirical rule that 68% of the score should be between +1 and -1 on any kind of z distribution. And so that's exactly how we would interpret it. There's a 0.68 probability that guests will order between 2 liters and 8 liters in the next hour. Or you could also interpret it as that them consuming something that's in that range of volume would be about 68% in terms of its likelihood. So that's how we can use the z-score to actually help make us smarter about whether something's unusual or not, about the amount of beverages that people are consuming or that we should have on hand. And actually that's the next example that I want to demonstrate. How likely is it that guests will order more than 8 liters? So now I have a situation where I want to find out what the probability that would be exceeding this level of 8 liters. Well, you can see we still want to go ahead and compute the z-score, which we actually did that in the prior example. We know the z-score is 1.0, and we know by looking at the table of z-scores for 1.0 that 0.84 of the probability for values are everything here to the left. But our question's asked more than 8 liters. So what we would need to do then is understand that since this is everything, all the possible ways or options that someone could consume liters from the beverage stand, and we've already identified 0.8413. We just need to take the 1 out of the proportion of that, and we'll see the remainder is 0.1587. And that should look familiar, because we actually calculated that on the other end. And since it's symmetrical, many of you probably didn't even need to do this math. You probably could have just said, well, it's going to be 0.1587 or 15% likelihood that, that they're going to consume more than 8 liters in the next hour, and you would be correct. Going to one more example here with the normal curve. If a manager wants to leave no more than a 5% chance of running out of beverages in the next hour, what would the restocking alert need to be set at? So you don't want to exceed, going dry, at the beverage stand any more than 5% of the time. So what level do you need? Here we're going to use the z-score table to find the probability and then figure out what the amount is. In this case, that's going to be our x. So we have a 5% chance of running out, but that also means that we have a 95% chance of fulfilling all the orders. This is really important logic when you're seeing these kinds of probability problems. Since you have a 5% chance of running out, meaning that you're up here in this area of the curve, we also do know, and the tables are really always going to be looking at something to the left of some point. We know 95% of the time we're able to handle the amount being consumed. So we need to find a z-score that's 0.95 probability that we will actually have sufficient stock. A little bit of a logic going on there. Now, since I know I need to find a z-score that's sitting at 0.95, how do I do that? I would actually go into the tables, and I'm actually going to be looking now at the actual output here for my situation where I'm trying to get 95%, and I can see that it's somewhere right in this range here. When I hit 0.945, going over to the next column of 0.05 gives me 95.05. So that's actually above the 95%. So I need some kind of a z-score value, which is going to fit right in between here. We know this is the very end of the z-score. And what row is that on? Is it on the 1.7 z-score, 1.8 z-score? No, it's on the 1.6 z-score. So that gives me the z-score of 1.6, and I'm going to round right in between here, 4.5. So a z-score of 1.645 is effectively the value that gives me a level that 95% of all of the beverages that would be ordered are to the left, and it leaves me 5% that would exceed. So that's helpful information because I'm trying to figure out how much beverage I need. So now I can use that other formula to convert this z-score to that actual value. And here's how that would be done. This is the situation where we know the z-score, we know the standard deviation and the mean. And so we would just plug that right into the formula. And we know that that's 3 times our z-score plus the mean. It's 9.935. So in other words, 9.934 or 5, I might have rounded up here or down here, liters of beverages in stock. There would only be a 5% chance of running out in the next hour. And so maybe I want to set the alert around 9 liters. In other words, I would tell whomever my workers are at that stand that, hey, once you hit 9 liters, you need to probably place a call to get resupply, because I don't want to be in that situation where we're out, however rare that's going to be. And it would be pretty rare based on all of this. So that's how we can work backwards and actually get a value for a level of beverage rather than just looking at it the other way around for a z-score. Now, this kind of logic using the normal probability distribution is very helpful, again, when you're looking at your own data, to ask questions about normal distributions of events. If IQ scores were normally distributed, we would expect a mean of 100 and a standard deviation of 15. This is just known worldwide about IQ scores. But you remember in the sample that we looked at in a prior session, we had IQ scores that were distributed across different schools. So can I use this logic to help me see our IQ scores? In fact, the average I see here in this sample is 1.128, and the standard deviation that we have is 17.6. Is that close enough? Is that normally distributed or not? That's the question that we're asking. Well, the answer is yes. We can run this using an Explore analysis in SPSS, and I'll show you how to do that elsewhere. And we can use some guidelines to help us interpret whether or not this is normally distributed. One of the things that I like to look at are the skewness and kurtosis. You'll find different guidelines for this class. I'd like you to use a guideline that if the skewness is plus and minus over 0.8, we would consider that to be a bit unusual, and a kurtosis of plus or minus 3. So here we can see that we have a skewness of minus 0.874. So it is looking like it's a little bit unusual. The kurtosis, though, is not at that level. We have a kurtosis at minus 0.02. So another way of interpreting these is if you divide the standard error into the statistic, it allows you to interpret it like a z-score. And you want to have values of your skewness and kurtosis plus or minus 2, which would be like interpreting it as plus or minus 2 standard deviations effectively within a range of skewness or kurtosis that you would expect. And so that's one other test that you can do. Down here I can see this is school A up here, school D down here. This looks very unusual here. I have a statistic of minus 2.65. So that's definitely outside of the guidelines. When I go ahead and calculate the skewness and kurtosis, I'm definitely way beyond a range of 2 standard deviations here, and same thing on the kurtosis. So this would lead me to believe that I have something very special happening with the IQ scores going on of students in school D versus school A. They may not be normally distributed. And what I do with that, it depends on the information or what decisions I want to make, but it's helpful to understand that there's something unusual happening with IQ scores in school D. Lastly, we can look at that by calculating a test of normality. This is the same KS and SW test that I'm going to show you how to get in SPSS. This is just another check. And what we're looking for is a non-significant test. What this is showing me here, I'm looking for non-significance on both of these. And for the first 3 schools, A, B, and C, they're non-significant. That's telling me that the IQ scores are fairly normally distributed, but school D is standing out. Something is unusual happening here. It might be an outlier, or maybe I just have some super smart kids, but they are somehow different, it looks like, at least in terms of their distributions from the other schools. And so that's one way that can help us interpret whether or not we're looking at normal data. SPSS can also very quickly calculate and convert z-scores for you. So I hope nobody is actually going to need to be using a calculator on their own data. There's a demonstration I'll show you in another video. Here is the IQ score 107. It will automatically convert it for you into a z-score. So I can tell this person's IQ is just slightly above average. You can see that 0.32, effectively standard deviations above, and this person is just slightly below at 90. This person's quite high at 131, z-score of 1.6. So they're a full 1.6 standard deviations above average intelligence, which is quite high. Now, the other reason why you might want to do that is there could be some point where you want to compare two variables. In this case, I have IQ score and I have depression, but I don't know a lot about the way depression has been measured. So in this case, if I go ahead and convert the depression scores into z-scores, they become interpretable on the same scale. This can be useful when you have different variables like height and weight that could be measured on very different scales. If you convert them into z-scores, they're more interpretable. You can actually do arithmetic on z-scores of combined scales in some ways that remove some biases, and so sometimes it's helpful. You just have to change your way you're interpreting the data. But that can also be a way of comparing things. You can also ask all the kinds of questions that you would about a level of depression, or how unusual is a level of depression above a certain value, the same way that we just did in the prior slides using this method. So the takeaway across the three, for dichotomous outcomes, the binomial distribution is super helpful for us to compare probabilities across a series of events or trials, like sale or no sale across 3 customers, for example, as we were looking at. Counts, the Poisson distribution is really helpful for us if we have events that might fit that. In our exploration so far, we've just looked at different ways of seeing whether or not the data fit a Poisson distribution, such as flight arrivals or arrivals at a hospital would be an example like that. So you can test for that. And then finally, when data are continuous or scaled, the normal distribution is really helpful for us to understand probability of events, because we get to use things like z-scores. Very helpful for us to interpret whether or not a certain level has exceeded or if we're within bounds on a certain level.